Unit 8.1, Acids and Bases. Topics in this lesson: definition of acids and bases, conjugate acids and bases, acid-base strength, polyprotic, polybasic acids and bases. What is an acid? What is a base? For thousands of years, people have described substances and chemicals as acid or base. Sour, tart foods typically contain citric acid, and the word acid derives from the Latin word for sour, acidus. The word base comes from the idea that when acids combine with certain substances, they form a solid salt. Hence, those substances act as a base or platform for the formation of that solid. Swedish physicist-chemist Svante Arrhenius described an acid as a substance that produces hydrogen ions, H+, when combined with water. He described a base as a substance that produces hydroxide ions, OH-, when combined with water. So an acid is anything that we put in water and produces H+ ions, and a base is anything that we put in water and produces OH- ions. Well, it turns out that that wasn't a very good definition. Some better definitions were created by Danish and British chemists Bronsted and Lowry, who independently created a new definition for acids and bases that was much more useful. A Bronsted-Lowry acid is a substance that can donate a proton. A Bronsted-Lowry base is a substance that can accept a proton. Now, just to remember, what is a proton? Well, if we have a hydrogen atom, it has one proton and one electron. If we take away the electron to make an H+ ion, all we have left is a proton. Conjugate base. When a Bronsted-Lowry acid donates a proton, the resulting substance is its conjugate base. Let's look at some examples. HCl, once it donates its proton, the thing that remains, Cl-, is called its conjugate base. HNO3, when it donates a proton, what remains is NO3-, that is its conjugate base. Skip to the bottom of our list. Notice water can donate a proton to become OH-, so water is an acid. Conjugate acid. When a Bronsted-Lowry base accepts a proton, the resulting substance is its conjugate acid. Let's look at some examples. Cl-, if it accepts a proton, then it forms HCl, that would be the conjugate acid. NH3, if it accepts a proton, it becomes NH4+, ammonium ion, which is its conjugate acid. Again, we see that water can accept a proton to become H3O+, an acid. Now, in a chemical reaction, when an acid and base react, both a conjugate acid and a conjugate base are formed. Let's look at our generic sample below. HA is some generic acid, and B- is some generic base. When HA donates its proton to B-, we're left with A-, the conjugate base, and HB, the new conjugate acid. We can look at a real example below. We have HCl and NH3. HCl is an acid. It will donate its proton to NH3. Once it does that, Cl- is left, that is the conjugate base, and NH4+ is created, that's the conjugate acid. Now we saw that water can act as both an acid and a base. This is called being amphoteric, meaning that something can act like an acid or a base. Well, how does it work? When water is in the presence of a stronger base, it acts as an acid and donates protons to the base. So NH3 is a stronger base than water, and so water donates a proton to NH3 to make NH4+. In the presence of a stronger acid, water acts as a base. Here we have HCl, a strong acid, donating a proton to H2O to make H3O+. Water acts as the base in this case. Here I have a table with several conjugate acid and conjugate bases. What I'd like you to do is pause the video and fill in on your own paper the conjugate acid-base pairs for each of these. Okay, let's see how you did. Well, HCl, if we remove a proton, we get Cl minus. H2CO3, if we remove a proton, we get HCO3 minus. HF, we get F minus. H2O, we get OH minus. H3PO4, we get H2PO4 minus. HCN, we get Cn minus. And H2Cr2O7, we get HCr2O7 minus. A conjugate acid-base pair will always be differing by only one proton. Let's try the other ones. Here we have NO3 minus. If we add a proton, we get HNO3. CH3COO minus. If we add a proton, we get CH3COOH. OH minus, we get H2O. HSO4 minus, we get H2SO4. ClO4 minus, we get HClO4. Br minus, we get HBr. And NH3, we get NH4+. Some acids are stronger than others. A strong acid is defined as an acid which gives away all of its protons. In a solution, there are no non-dissociated acid molecules. There are 7 strong acids: HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. You should learn these. Here we see an example of what happens when we have a strong acid. The strong acid dissociates completely. So for HCl, if we have 1 molar HCl, once we put it into the water, we have no HCl, we only have H plus and Cl minus. Now, in contrast, a weak acid dissociates only partially. So here we have H2C6H6O6, which is ascorbic acid. It's a weak acid. So if we start with 1 molar of ascorbic acid, only some of it will dissociate. And we'll only have maybe 0.02 molar instead of 1 molar that is dissociated. All acids that are not strong acids are classified as weak acids. There are way too many of these to even list or even try to learn, but just keep in mind, if you have an acid that is not one of the 7 that you were supposed to memorize as a strong acid, it is a weak acid. The conjugate base of a strong acid is a very weak base. The conjugate base of a weak acid is a relatively strong weak base. There are also strong and weak bases. Strong bases are mostly soluble in water and add hydroxide ions directly to a solution. Hydroxide is able to readily accept a H+ to become water. The strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide and cesium hydroxide, beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. 2 of the strong bases are relatively rarely used. Beryllium hydroxide is rarely used because it is poisonous. All the bases that are not strong bases are classified as weak bases. Again, there are so many examples of this. The conjugate acid of a strong base is water. This is because all of the strong bases donate hydroxide directly, and the hydroxide accepts a proton to make water. The conjugate acid of a weak base is also a weak acid. Polyprotic and polybasic acids and bases. Some acids can donate more than 1 proton. Monoprotic, diprotic, and triprotic. Monoprotic acids are those that can only donate 1 proton. An example is HCl. A diprotic acid is one that can donate up to 2 protons. H2CO3, or carbonic acid, is an example of that. Triprotic acids can donate up to 3 protons. An example is H3PO4, phosphoric acid. It's important to realize that with the exception of sulfuric acid, all di- and triprotic acids are weak. This means that they do not dissociate completely by giving away all their protons. So just because phosphoric acid can donate 3 protons, it doesn't mean it will donate 3 protons if we just put it in the water. However, weak di- and triprotic acids can be forced to donate all of their protons in the presence of a strong base. The base will basically grab the protons from the acid and strip them off. Some bases can accept more than 1 proton. A monobasic base, such as NaOH, can accept 1 proton. A dibasic base can accept 2 protons, like calcium hydroxide, and a tribasic base can accept 3 protons. An example of this is the phosphate ion, which can accept 3 protons to become phosphoric acid. For bases which contain hydroxide, each hydroxide can accept 1 proton.